Hi, everybody. My name's Derek Bingham. I'm a developer advocate at AWS, and welcome to today's talk, all about 5 design patterns to build resilient applications. So today, over the next 35, 40 minutes, I'm going to go through an application, and I'm going to show you what patterns you can use to implement and build out a more resilient application framework. So, as well as that, I'll just say up front that I apologize for all the really bad jokes you'll hear today. You'll know more of what I mean as we go into the talk. Also, we'll have live Q&A. So if you've got any burning questions about what I'm talking about today, please enter them into the chat and we will respond as we go. So without any further ado, let's get into it. There we are. So let's start with a quote. So the quote I have for you today is from Dr. Werner Vogels, our CTO at Amazon. Failures are given and everything will eventually fail over time. So when I talk about this quote, I talk about it in terms of how to build out your modern distributed cloud native applications. As you build them, you inevitably go over different pieces of hardware, different networks, using different stacks to build out those applications, and in any one of those components can fail at a time. Now, this isn't a bad thing. This is actually asking you, when you're building and designing that application, to think about the failure modes that that application will have to adopt with and grow with over time, so that when a particular component does go down, as it inevitably will, how your application can recover and continue to serve its users. So today, that's exactly what I'm going to do. I'm going to show you 5 patterns that you can implement to make that distributed application resilient to failure. And I'm also going to show you one practice. So the patterns I'm going to show you are timeouts, graceful degradation, retries, exponential backoff, and circuit breakers. And the one practice I'll show you at the end is chaos engineering. So let's start by meeting the application that we're going to build today. So here I have a .NET application, and the .NET application itself is all running in JetBrains Rider here. So my IDE of choice is JetBrains Rider. If I have a look at the application itself, you can see that up in the top left, I'm going to scroll there. We've got a React app inside the client app folder. And inside that source directory, I have got a component directory, and inside that, a fetch data.js. So this is the main component of my React app. So the fetch data.js has got a constructor, it's got a table in it that renders jokes, more on jokes in a second. And if you scroll down a little bit more, you'll see there's a button and some contents. But the really important function is this: populate joke data. You'll see that the function ultimately calls an API/joke endpoint, gets some response in JSON, and then renders that response. So that is the React app. Also, we have an API. So this is what the React app is hitting. It's a .NET controller. It defines a joke client, and in the joke client is, if we have a look at it now, defines a joke URL. So this is a third-party joke API that this client calls. And in here, we've got an HTTP client, which is how .NET does REST calls. It hits the joke API, gets a response in JSON, and then serializes that JSON back out to the React app. Now, the serialized JSON, this is the object that it's serializing. It's got a joke, and it's got setup, punchline, and source. And we'll go more into that in a second. So this is the app running. So this is my little React app. Why are monkeys good at sports? They're born champions. If I hit refresh, it'll give me another joke. What's the object-oriented way to become wealthy? Inheritance, of course. And then finally, how many programmers does it take to change a light bulb? None. It's a hardware problem. As well as the UI, here's my API. So I'm showing you what the little joke client is hitting, and it comes back with the joke as part of a setup, the punchline, and the source. Currently, the source is always going to be third-party API because that is what I'm hitting. So that's the application that I'm building. So let's go start applying some of our patterns to this architecture. So the architecture itself, you can see, has a little React application. The React application hits the .NET microservice, so that controller with the joke client. That then acts as a proxy into a third-party joke API, which could be running locally on my machine. It could be running in the cloud somewhere that serves me back jokes back to my .NET microservice, and then proxies that back to my React application that renders the joke. So that's all well and good, but what happens if my third-party joke API runs into some issues? And today we're going to simulate those issues by having some random failures inserted into the joke API. So what will happen typically? Well, a client will make a request into the .NET microservice. That will then proxy that request into the third-party joke API, and it'll just sit there waiting. It may retry, but that will just sit there. And then, of course, the React web application would sit there as well, just waiting for that response. So maybe another client will put another request into my .NET microservice, which again will proxy that into the third-party joke API, which is already under load. So that would then delay that response, which would delay that response. And then ultimately, it would bring down not my .NET microservice as well. And then the client would inevitably make another request into the .NET microservice, which is itself under load and is not very happy because of all the requests that are waiting. So a first pattern that we can try to negate this sort of problem happening is timeouts. So let's go back into the code and build out what timeouts would look like. So if I change that so you can see, go into the code here, and let's see what we can do. So the first thing I need to do is I need to add a timeout to the HTTP client. I do this in .NET by just adding a property to the HTTP client, and the property in this case is called timeout. So the timeout itself, I can set for a time span. For this one, it makes sense to go a time span not of 0, but of seconds. And for this, I'll probably set a time span of 5 seconds. So what this is doing, it's basically saying that for this client, then have a timeout after 5 seconds. So if I do a request, how many programmers to try to change a light bulb? If I hit that request, if the request takes longer than 5 seconds, it will time out. So here it didn't take longer than 5, so I got a response back from a third-party API. If I do it again, loading, it may take more than 5 seconds this time. It has. So the UI is actually frozen as it waits for a response. But then if I see what's happening in my .NET microservice, if I do a refresh a couple of times, it's coming back from a third-party API, okay. But then, boof, what I get is a timeout exception. So what's happened here is my .NET microservice is requested my third-party joke, and after 5 seconds, it's timed out. So that is how to implement timeouts. Now, timeouts in themselves are quite a rudimentary way of handling the API. So how can the next pattern, and I'm going to call this pattern 1A, how can I go about improving that timeouts? So currently the timeout that we're seeing is just spitting an exception out. We're not handling it in the UI, but how can we get more control out of that particular timeout? So let's go into the next pattern and get more control over that timeout. So back into my code again. So this time I'm going to get rid of the original, I'll call it the simple timeout, put the client code back to the way it was. And for this one, I'm going to start using a library, this is the .NET library called Poly. So Poly is a resiliency library that we can use. So every language out there will have a resilience library. Poly is just the one for .NET. There's a resiliency for J if you want to use Java, and other languages have a similar library. So in Poly, I'm going to set a timeout, an asynchronous timeout of, again, 5 seconds. But now I'm going to wrap my request and response code in an anonymous inner function. So if I go policy dot execute async, and then inside that I'm going to have an anonymous async function, which is going to have a cancellation token. So CT I'm going to define as my cancellation token. So what it's doing is I can cancel individual tasks with inside this anonymous function. So all I'm doing now is pulling that code up into my function, like so, and just finish up the indenting here. And so now this function is going to execute, but I need to define my cancellation token that will give me the control over async tasks within this function. So get async can have a CT, a cancellation token, as can the response. So I can control that cancellation token and give you a bit more granularity of control inside that timeout. If I go back and rerun this application, you'll see what that looked like. So back inside my joke app API, once it spins up, you will see that where monkeys great at sports, they are definitely born champions. Tell me another, and refresh. Oh, came back within 5. Refresh again, and we go back, and let's just refresh this. Refresh, they're all coming back really, really quickly now. I was away. So my third-party API, which remember I put in a random delay in, and here we go. It's greater than 5 seconds, so we get this delegate executed asynchronously throughout the timeout policy. So it did not complete within the timeout. So again, the exception isn't caught because I'm demonstrating it here, but it gives you a better granularity of control over the timeout. So that is 2 ways that you can do timeouts, either by using a timeout within the HTTP client itself as a parameter, or by using a third-party library like Poly. And what we'll do for the rest of these patterns, I will continue to build out how we can use Poly to satisfy them. That's that. Next is pattern 2. So pattern 2 is called Graceful Degradation. The code expands that out a bit, like so. So let's build out what Graceful Degradation will look like using the Poly library. So from Poly, the next thing I need to do is I'm going to define a fallback policy. So what a fallback policy is the policy that Poly will call if my original policy throws an exception. So this fallback policy will return me a list of jokes. So IEnumerable is a list of jokes. And what it has to do is has to handle a type of exception. So I'm going to be very generic here and say handle exception, well, generic exception. Once I've defined the exception it's going to handle, the next thing I will need to do is say, okay, what am I going to do when I fall back? So this is the fallback async method that I'm going to define. Again, this takes an enumerable, so a list. I'm just going to tidy this up so you can see it. Next line. Again, this takes an enumerable of jokes. And inside the fallback async, I'm going to do another anonymous function. And inside this anonymous function, I'm going to return a joke or a fallback joke. So what this is doing is, again, async the cancellation token into anonymous function, enter new list of jokes. And for this list, I'm going to, for the sake of everybody watching my typing, only have one joke to be returned. And so if you remember, my joke object has a punchline. It also has a setup and it has a source. So we'll define those inside my joke object. Setup is a string. Punchline is also a string. And then source is a string, consistent. So let's think of a joke, another marvelous joke. So let's have a band joke. So I'm in a band. It's called 123 megabytes. We haven't, triple punctuation, had a gig yet. Now the source is going to be fallback. So this is going to show us when in the UI when we have hit the fallback. So next thing I need to do is I need to pass that policy into a wrapper. So the policy wrapper is how I can pass different policies, almost chain them in an order of precedence. So what I'm going to wrap async is the fallback policy, which I've done there. Then inside that, I will wrap the policy. And so now, once the policy fails and throws an exception, we should then get the fallback policy. And the last thing I'm doing, I need to pass the policy wrapper to the execute async. So once that is done, we are going to gracefully degrade the API, so the endpoint. So let's refresh the page. What's the two hard things about computer science? Cast and validation, brown things, and that. We refresh again. And we're waiting for 5 seconds. Oh, here we go, fallback. So I'm in a band called 1023. We haven't had any gigs yet, and that's the source of fallback. Refreshing the back end to see what happens in the API calls. Again, and there we go. We're coming to fallback. So as you can see, we refresh. If we hit more than 5 seconds, we show the fallback. If we hit again, the API is working, we get a normal response. If we refresh again, we may then get the fallback if it's over 5 seconds. So what it's doing is over time, if the API is having problems, we gracefully degrade it. So that's the second pattern. So let's go back. The next pattern is third pattern is retries. So what we've had our timeouts. So we have set the maximum time that you can wait for a response. We've had graceful degradation. So we've said if we've got an exception inside that timeout, show something else. And then pattern 3 is retries. So all about how many times we can retry a particular endpoint to see if it will give us the response that we need. So the next side, I've just changed the timeout to be 2 seconds, not 5. Otherwise, we could be waiting here for a while. And what I'm going to do now is define a retry policy. So the retry policy is, again, another policy. This time, the handle is again going to be in exception. And on exception, you define what your retry async method is going to look like. So remember, the last one was a fallback async. This one is a retry async. So we're going to set a retry count, which is a 5. And once the retry count is set, we're going to add that policy to our policy wrapper. So if you remember, it's a concatenation of all our different policies. So what we're saying here is if the original policy doesn't work, do a retry of that policy. If that doesn't work 5 times, then hit our fallback policy. So that's what that policy wrapper is doing. So let's see what that looks like in our app. So let's restart our app. Starting our app up. And so let's refresh. Thinking, loading. So I tell you, UDP joke, you might not just get it. These jokes are great. How many programs does it take to change light bulb? It's a hardware problem. Tell me another. So far the API is behaving. So now it's loading. Remember, we're hitting that API. If it doesn't respond, then we're going to do retries up to 5 seconds, up to 5 times. And if that doesn't get back to us, we should then retry, get our fallback. So here we're loading again, we're retrying. Remember, they'll timeout. Each request will timeout after 5 seconds. And here we are, we're in fallback. So what's happened is the API has been hit 5 times. It's timed out. Every timeout has been 2 seconds. So 10 seconds in total. And if that didn't work, we hit our fallback. So that's the retry pattern. So with the retry pattern, we can have more granularity over our retries, over our timeout. But again, we always have that graceful degradation, that fallback in place. The next after retry is exponential backoff. So the next problem that we've got is exponential backoff. We're going to think about exponential backoff as it is a improvement over the retry pattern. Why the retry pattern? Because if you think about the retry pattern, you can define as many retries as you want. So if you're a client and you're hitting this third-party API 5 times, that seems fine. But just say there is 100 clients. The retry pattern in its very basic form is creating a distributed denial of service attack on that third-party API. So it's not recommended, but it's definitely needed before you can start understanding the more complex patterns that I'm going to talk about next. So the first one of those is the exponential backoff pattern. So if you think about exponential backoff, I've got a little slide for this. So the exponential backoff pattern, let's think about it. So the React web app goes to the .NET microservice, proxies it into the third-party app. Third-party app, we start retrying. The retry does not work. We wait 2 seconds before we then retry. Instead of waiting another 2 seconds, we actually increase our wait time exponentially, hence the name. So the next one is 4 seconds. Then we wait 8 seconds. And then finally, we wait 16 seconds before we might get a response from a third-party API. So what that's doing is actually distributing the load into our third-party API. So it's a better way of doing retries. So let's have a look to see what this looks like. So here we are back in our retry policy. So exponential backoff is simply changing this retry policy and adding that math factor to it. So what we want to do is apply a wait and retry async, and then define the wait mathematics, if want of a better word. So what we're going to do is we're going to try 3 times, and then each retry attempt we're going to do over a particular time span. So that time span, we're going to have a seconds math par. So we want an exponential. So what we're going to do is a math par of 2, and then retry attempt again. So it's going to give us that 2, 4, 8, 16 time frame that we looked at in the slides. If I just tidy up the retry attempt, I can spell. There we go. That should do that, and that is our new retry policy. Just tidy up the code, save it, and see what this looks like. Rerun the client application and see what the exponential backoff looks like. So refresh. So as you see, we're loading. We are calling it. We time out after 2, we'll retry after 2 seconds. Time out after 2, we'll retry after 4 seconds, all the way up into 14 seconds. And then if we hit 14 seconds without a successful request, we will get this, which is the fallback. But as we retry, we should then get successes as well. So let's wait for that. It could be bit. We're retrying. We're waiting for 2 seconds. Retrying. Waiting for 4 seconds. Retrying. And there's one. There's only 2 hard things in computer science. And then there's our werewolves joke. We're not werewolves. So what's happened here? We've implemented an exponential backoff. So what's next? So as there is an issue with retries and or denial of service happening with exponential backoff, there's also something to be aware of, and that is the ability for the retries to cluster as well. So if you think about the way we implemented the exponential backoff, we did a par of 2 math operation before retries. Now, most people will probably end up doing that. And what will happen is the retries themselves will cluster, and in effect, they will negate the ability of the exponential backoff to spread the load across the third-party API. So the recommended approach to actually spread that load is by using the jitter pattern. So the jitter pattern is mentioned, if you want to read more about it, is in our builders library, which I've got the URL there. And it will go into more detail of what the jitter pattern is, but in essence, it's all about spreading that retry, that exponential backoff into a more random nature. So I've got some code around that as well, and we can implement that. So let's think about exponential backoff with jitter, which is I'm calling pattern 4a. So let's just make this a little bit bigger. There we go. So what's this going to look like? So if we go back into my wait and retry async, I need to improve this to add in that randomness. So I do this by adding a time span of millis, and it's a new random, and it's going to be between 0 and 1,000. So 0 and 1,000 millis. So it's going to give us a plus or minus 1 second randomness towards our retries, and that's it really. And that's all we need to do, because if you think about it, then we're less clustering because it's purely a random retry. So the next one I'm going to talk about is circuit breaker. So we went through what I almost call the 3 retries. So the retry standard, the retry with exponential backoff, and then retry, exponential backoff, and jitter. The next pattern we're going to talk about is circuit breaker, and I've got a little diagram to just explain that as well. So circuit breaker is where you've got obviously your request coming through proxy through your microservice into your third-party joke API, which then the third-party joke API has that random injected failure that we have. It'll retry again because we've done our exponential backoff with Jitter. It'll retry after X number of seconds, and then you keep hitting this service. It's still broken. So all of those retries, they're just really useless. So what we can do is completely negate the load on the third-party API server by implementing a circuit breaker. So a circuit breaker, once you implement a circuit breaker, you specify inside that circuit breaker how many minutes to not push the request through to the third-party API, but rather just return a dummy response. So, and then after the minute is over, the circuit breaker will go down, and you will be able to then hit the endpoint again. So let's see what that looks like in code. So make it bigger. So in this, we were going to add our circuit breaker. So what I'm going to do, I'm actually going to hide this up a bit because it's a little bit messy. So I'm just going to do a quick refactoring. So what I'm going to do, I'm going to, because with circuit breaker you need state, so I'm going to pull the state up of the policy wrapper in as a class field. So if I look inside that jokes method, that jokes method is called for every request. So what I want to do is define my policies in a construction of the client because it's a singleton rather than at every instantiation. So sorry, every time it's called. So I'm just defining a class variable called wrapper, and then I'm going to move all of this code here up to be called only when the joke client is constructed. So that will enable me to, only call it once, but also if there's any state inside this policy, I can maintain it inside here as well. So I'm going to call it init policies is the method that's going to contain all of this information, and I'm going to move the actual method call from the jokes method inside the actual constructor of the joke client. So that's nice and tidy now. So what I need to do is what we're actually here for is to build out that circuit breaker. So the circuit breaker itself, we're going to define as another policy. So first of all, we define the circuit breaker policy, and we're also going to define a circuit breaker fallback. So we can tell the user when the circuit breaker has actually been evoked. So first we do the circuit breaker policy. Again, we have called policy. For the circuit breaker, again, we're going to handle an exception for any general error that happens. And then what's going to happen when this exception occurs? We're going to define a circuit breaker. Just tidy this up a bit, just indent it a bit so you can see it. So the circuit breaker itself, we're going to say if they call the API 5 times, in a minute, it's going to break that circuit for 1 minute. So if you call the API, it has 5 exceptions, then we're going to implement the circuit breaker for 1 minute. And then how are we going to know that a circuit breaker is in place? Well, we're going to implement a circuit breaker fallback. And this is what we're doing now. So circuit breaker fallback equals policy. So the handler for this policy, the fallback is obviously like all our other fallbacks is going to return a list of jokes, which is going to be one joke. But it's going to handle, and this is a little bit different, we're going to handle a circuit breaker exception. So it's only going to be invoked when we get when the circuit breaker fails. So let's write that. So handle circuit breaker exception, which is called broken circuit. And then once that appears, let's then do our fallback, and inside our fallback, again, we're going to have another anonymous inner function returns the jokes. That is our fallback joke. So I get to think of another joke, which is exciting. So this is exactly like the other fallbacks where we have an anonymous inner function that simply returns a list. That list is a single joke. Oh, that's over there. I need to tidy that up a bit, indent it. There we go. And let's define the joke. New joke. Inside the joke, we need a setup, a string, setup, punchline, also string, and then our source. So this will be from our circuit breaker. With single K, thank you. So another joke. Oh, alrighty. So why did the developer go broke? Well, obviously it's something to do with cache. Because they used up all their cache. Kaboom tish. Just make sure I've got all the looking all right. Tidy it up a bit. Yep. So and finally, of course, we add this into our wrapper. So concatenate in our circuit breaker and our circuit breaker fallback. Okay. So once that's in, we can save and we can redeploy and run it in our client app. And hopefully we will get to our circuit breaker fallback and see how the circuit breaker actually works. So if we redeploy it, wait a couple of seconds, get back into our application and hit the refresh. Oh, that was very quick. So the API worked first time, of course, there. We're hitting loading. We're retrying. Remember, we have to retry 5 times before the circuit breaker comes in. So that wasn't 5 times. No. Try another. Nope. Of course, it's always the way when you're trying to test a particular use case. Oh, this is a bit more. This looks like we're trying to retry 5 times. Exceptions. We need 5 exceptions, and then our circuit breaker is going to come into force. This looks good. No, oh, this is it. Yep. So source circuit breaker fallback. And so now if we invoke the API, we should then get our circuit breaker right away because it's not going to the third API. It's not going to get any exceptions from that API or retry that API. It's just going to go directly from our circuit breaker. So that's the power of a circuit breaker. And then after a minute, of course, it will go away and we'll start hitting our API endpoint again. So that's the circuit breaker. That worked. So that there are 5 practices that we went through today to try and build a resilient app. The last part I'm going to address today is the practice. So the practice I'm going to talk about is chaos engineering. So throughout our demos today, I had that third-party joke API. Now the third-party joke API had injected some random failures into it. So we could see it failing, so we could test and build out our patterns. So that practice is called chaos engineering. So chaos engineering is not only injecting failures into a service or stressing a service, it's also observing how that service behaving under that stress, and then using that to improve the service. That is inevitably what chaos engineering is all about. It's all about improving the resiliency and performance of your systems by uncovering those hidden issues, exposing the blind spots, or the things you don't know about, and a lot more besides. And why is it difficult? So traditionally, you'd have to stitch together scripts and tools to try and bring down services at a particular time, or you have to install agents and complex libraries to get started. Also, it's hard to implement reasonable tests in a reasonable environment. When I say reasonable, like production, because injecting chaos into production is probably not what you want to do. And it's also, so that makes it really hard to reproduce real world events. So we come up with last year the fault injection simulator. So this is a way to inject chaos into your system. So I'm going to give you a quick demo of how you would use that fault injection simulator with a third-party API. So let's say that the third-party API we've been using, the Joke API, is running across a suite of EC2 instances. Let's see what we would do to inject chaos using the fault injection simulator. So we talk about experiments. When we're talking about chaos engineering, when you inject experiments into our running application. So this experiment, we're going to stop instances. Now, just to reiterate, everything I do here actually stops the instances. It actually works on real services. So this is not a mock or anything. This will actually happen. So disclaimer there. So we call an action called stop instances. Inside that, we give it a target. And inside the target, we give it some parameters. So we're saying that for all the instances, we're going to stop them for 1 minute. Once we've defined the target, we next need to say if there's any tags. So all of my API servers, EC2 instances, I've tagged with EC2. Oh, sorry, with API. So that way I can be very targeted in what I want to do with this experiment. Once I have defined the experiment, I can create it. And once it's created, you can see that these are my API EC2s, and they're all running. I can then run my experiment. So I start my experiment. You get lots of warnings because this, as I say, this is real. This is really happening. And the experiment will start to run. So as you can see, the experiment now is pending. The EC2s will run, but if I keep refresh, we should see them stop. So see, this is the experiment. And now it's running. So there we go. So all the instances have now stopped, and they will stop for 1 minute because that's what I've defined my experiment. So then I can build my application and test my application to see how it's handling the issue of having no servers there. So as well as stop instances, there's all swathe of actions you can use with the fault injection simulator. Where you can, if you're using containers, you can drain container instances. You can do a lot of different actions with the fault injection simulator, not just the very simplistic action of stopping a server, which I'm doing. So this is back inside our app. So we've waited a minute. If we then refresh, there we go, our instances are back up. So that's showing us that how targeted the fault injection simulator can be, quite granular. You can define time spans that you want the chaos to actually exist in. So if you want to test this in production, you might particularly test specific services for a specific time frame at a specific time of day. So that's cool. So that's today's talk. Thanks for staying. So the 5 patterns I talked to you today were timeouts, graceful degradation, retries, exponential backoffs, and circuit breakers, and then the 1 practice. The code for today is up on my GitHub repo if you want to have a look at it and if you're interested. If you're interested more on chaos engineering, read these articles by Adrian Hornby, a colleague of mine, where he goes into a lot more depth. There's also some free AWS training that you can get here if you want to know more about AWS. And also, please complete the survey. Give me feedback on how you found the talk today. That would be really appreciative. And also, if you have any particular questions, please tweet me, reach out, and yeah, I'll see you next time. Thanks for sticking around. Really appreciate it, and I hope you enjoyed the talk. Thanks very much now. See ya.